In the previous two lectures, you have seen actually the two vector operations, gradient of a scalar function and divergence of a vector function. Now we will see the curl of a vector function in orthogonal curvilinear coordinate system. Actually, this curl operation is also defined for a vector point function as a divergence is defined for a vector point function. But there is a difference. As you know, divergence of a vector function is not a vector, but that is a scalar. But curl of a vector function is a vector quantity. And how it is a vector quantity, how it will be defined in orthogonal curvilinear coordinate system, all these things we will discuss in the present lecture. So for this, let us consider a vector point function as we have considered earlier f, and this f is actually a function of the curvilinear coordinates u1, u2 and u3. As you know, these u1, u2, u3 are in general the orthogonal curvilinear coordinates in orthogonal curvilinear coordinate system. Now, as any vector in general can be expressed as the sum of its components, so you may write f equal to f1 e1 hat plus f2 e2 hat plus f3 e3 hat. These things you have seen so many times earlier. Now, curl of vector f is also denoted by the symbol del cross f. In other words, you can say that the operator del cross means curl. So when you write curl of f, it means you will operate del cross operator on the vector function f. So you can see as f is equal to this much, so del cross f will be what? This will be simply del cross f1 e1 hat plus del cross f2 e2 hat plus del cross f3 e3 hat. Now we will evaluate the three terms in the RHS of equation 1 separately, and then after substituting all those values in this equation 1, we will get the expression for curl of f. So let us try to evaluate the first term. So you can see here now del cross f1 e1 hat, del cross f1 e1 hat. As you know, this e1 hat unit vector, this e1 hat unit vector you have seen in the earlier lecture that this is simply equal to h1 del u1, h1 del u1. Since you can say that this e1 hat is equal to the scale factor h1 times del u1, gradient of u1. You know it. You have seen these things in the previous lectures. So instead of the unit vector e1 hat, I have written here h1 del u1. Now you can see inside this bracket on which this curl operator is operated, that is del cross is operated, there are actually the product of two functions. First one is f1 h1 and another is del u1. So we will follow the rules of differentiation for product of two functions here, and so following that rule you can write it. This is del f1 h1, that is gradient of f1 h1 cross del u1, and plus second term will be f1 h1 del cross del u1, f1 h1 del cross del u1. Now see here, this del f1 h1, it means gradient of f1 h1, and again this del u1, del u1, you can see from here, this may be written as e1 hat over h1. So instead of this del u1 vector, I am just writing e1 hat over h1. e1 hat over h1. So in right here e1 hat over h1 and plus this is in fact a curl of gradient of a scalar function, but curl of gradient of any scalar function is always 0, so this will be 0. You can say that this del cross del u1, this is equal to 0. So second term vanishes, only the first term remains non-zero. Now you have seen the definition of gradient of a scalar function in the previous lecture, and on the basis of those concepts you can write the expression for del f1 h1. Here the function whose is gradient whose gradient is to be find is f1 h1. So from the definition of gradient of a scalar function, you can write the expression for this del f1 h1. So what will be the del cross f1 e1 hat? We are just evaluating this term, and you can see in RHS there is del f1 h1, and from the definition of gradient of a scalar function you can write this equal to e1 hat over h1. You have studied these things in the previous lecture. Del u1 f1 h1 plus e2 hat over h2 del u2 f1 h1 and plus e3 hat over h3 del u3 again f1 h1. This is actually the expression for gradient of f1 h1. You know it. And then we have to take the cross product with e1 hat over h1. So I am writing it here. This is cross e1 hat over h1. Now you know in orthogonal curvilinear coordinate system, e1 hat cross e1 hat, this will be 0, but e2 hat cross e1 hat, this is equal to minus e3 hat, you know it, and e3 hat cross e1 hat, can you say what will be this? This is actually equal to e2 hat. So see here, when you will take the cross product of this first term with e1 hat over h1, then that will be 0, because here unit vector is e1 hat and here also the unit vector is e1 hat, but e1 hat cross e1 hat is equal to 0. So the first term will vanish, and so you can write del cross f1 e1 hat. This will be equal to, first term is 0, but e2 hat cross e1 hat, this is minus e3 hat. So you should write it minus e3 hat over h1 h2 over h1 h2 and del u2 f1 h1 del u2 f1 h1. Now we will take the vector product of this third term with E1 hat over H1. But you know E3 hat cross E1 hat is equal to E2 hat. So this will be in fact plus E2 hat over H3 H1. H3 H1 and del U3 operated on F1 H1. So you may write it in this arranged manner. This is E2 hat over H3 H1 del U3 F1 H1 and minus E3 hat over H1 H2 del U2 F1 H1 and say this is equation number 2. So you can see we have easily evaluated the expression for this curl of F1 E1 hat. This is curl of F1 E1. Del cross means curl. So this is curl of F1 E1 hat. Now with an analogy of this result, you can write directly what will be the expression for curl of F2 E2 hat and curl of F3 E3 hat. In the light of this equation 2, you may write directly the expression for those vectors. So let us try to write. But before writing the expression, see here, when you write the curl of F1 E1 hat, that is subscript is 1, then you can see here unit vector is E2, not E1 in any term. And actually, in scale factors, one should be H1 for this F1 and another should be H2 and H3. So seeing these things here and by an analogy, I am just going to write the expression for the other two terms defining the curl of vector F in equation 1. So I am just going to write the expression for del cross F2 E2 hat and del cross F3 E3 hat in the light of the result obtained in this equation 2. You can see. So let us write it similarly. Similarly, you can write del cross F2 E2 hat. F2 E2 hat. This will be in fact E3 hat over H1 H2 del U1 F2 H2 and minus E1 hat over H2 H3 and del U3 F2 H2 and say this is equation 3. And in similar manner you can write del cross F3 E3 hat. This will be what? This will be E1 hat over H2 H3 del U2 F3 H3 and minus E2 hat over H3 H1 del u1 f3 h3 f3 h3. This is equation 4. So you can see we have evaluated the three terms in RHS of equation 1. So when we will substitute all these values in the RHS of equation 1, we will get the expression for curl of the vector function f. So substituting these in equation 1, we get, you can see in equation 1, you can see there is curl of f, which is equivalently written as del cross f, and that is equal to, see the equation number 1. This is del cross f1 e1 hat del cross f2 e2 hat plus del cross f3 e3 hat. And let us put the value of these things, that is del cross f1 e1 hat, del cross f2 e2 hat, and del cross f3 e3 hat from equation 2, 3 and 4. So you can see this will be e1 hat over h2 h3. You can see the values, del u2 f3 h3 and minus del u3 f2 h2. Here I have actually taken this e1 hat over h2 h3 as a common factor. You can see all the terms and take this e1 h2 h3 as a common factor, then this term will remain here. And similarly plus, now take e2 hat over h3 h1 as a common factor, and this will be del u3 f1 h1 and minus del u1 f2 h3. You can check it, f2 h3. And I am just writing the next term in another page. This will be plus e3 over h1 h2 del u1 f2 h2 and minus del u2 f1 h1. In fact, you can see all these expressions and take the common terms as common factor and then arrange the terms. So after arranging all those terms, you get this expression. Actually, this result is written in a convenient form, in determinant form, and that form can be remembered easily. This form of the definition of curl of f is not so easy to remember, but when you will express this expression in determinant form, that will be very easy to remember. So you can write it in determinant form. In determinant form, you can write curl of f, which is equivalently written as del cross f. That can be written as 1 over h1 h2 h3. h1 h2 h3. H1 E1 hat, H2 E2 hat, H3 E3 hat, and del del U1, del del U2, del del U3, and F1 H1, F2 H2, and F3 H3. You can check the above expression for curl from this determinant, and this is very easy to remember. So I will suggest you must remember this expression. Actually, the deduction of this expression or proof of this expression is not so important as we need its remembering. You must remember it because you will find its application at several places, and if you remember this expression, you can easily find what will be the expression for curl of f in different orthogonal curvilinear coordinate system. You have to only evaluate the proper value of h1, h2, h3, that is a scale factor. Now, after getting the idea of gradient and divergence of a scalar function and a vector function, we are able to find a very we can find the expression for a very important operator, and that very operator is known as Laplacian operator, or simply you can say Laplacian, because this Laplacian operator is a very important operation of mathematical physics which is used at several places while discussing the course on physics in any branch. So let us try to find what will be the expression for Laplacian in the orthogonal curvilinear coordinate system. Laplacian. You know, Laplacian operator is denoted by the symbol del square, and our aim is here to find the expression for Laplacian operator in the general orthogonal curvilinear coordinate system. So you can see, if you write the expression del square phi, where phi is actually a scalar function, then this del square phi you may write it as del dot del phi. Del dot del phi. Now, this del operator in terms of orthogonal curvilinear coordinates, you have seen earlier that this del operator is defined as E1 hat over H1 del del U1 plus E2 hat over H2 del del U2 and E3 hat over H3 del del U3. This is expression for the gradient operator or del operator, del. And gradient of phi, del phi, you know, I am writing it here. This is del phi, you know, is defined as E1 hat over H1 del phi by del U1 plus E2 hat over H2 del phi over del U2 plus E3 hat over H3 del phi over del U3. Now, operate this operator, that is del operator, on this function which is inside the second square bracket. You can see we can write this expression in a particular form in this way, and that this is equal to 1 over h1 h2 h3. See here, you can see the algebra. I have taken the factor 1 over h1 h2 h3, and that will be managed in the in the terms inside the bracket. You can see it here, and this will be del u1 h2 h3 over h1 del phi by del u1. You can check it. In fact, when we will operate this part e1 hat over h1 del u1 on the first part, then this term will appear here. Actually here, when you will take actually this h2 h3 as a constant factor, let us say, then this in fact h2 h3 will cancel, and h1 and h1, that will be h1 square, that will remain here. So we can write like this. And similarly you can write the second term del u2 h3 h1 over h2 and del phi by del u2 and plus del u3 h1 h2 over h3 and del phi by del u3. You can write it. And since it is equal to del square phi, so if you want to write the expression for del square, then just omit phi everywhere inside this bracket, and then you will get the Laplacian operator. So in terms in this condition, we can write the expression for the Laplacian del square in this way. This is 1 over h1 h2 h3 h1 h2 h3 del u1 h2 h3 over h1 del u1 plus del u2 h3 h1 over h2 del u2 and plus del u3 h1 h2 over h3 del u3. This is actually the expression for the Laplacian in orthogonal curvilinear coordinate system. And you will find the use of this general expression when we will discuss the particular orthogonal curvilinear coordinate system. In fact, we will find the scale factors in a particular coordinate system, and then you will get the expression for del square in Cartesian coordinate, in a spherical polar coordinate system, and in cylindrical coordinate system. And that are actually used invariably in different places, in different concept of the physics. So this is a very useful operator, and its use in different coordinate system is actually take place. And so this general expression will help you to remember the expression for Laplacian in different orthogonal curvilinear coordinate system, which we will see in the forthcoming lectures.